Thank you. Thank you very much. And thank you, everyone, for being here and for your attention today. It's always a pleasure to be here. And so I gladly accepted the invitation to be part of COBS, as well as there's the meeting tomorrow. So thank you, everyone. And COBS has been fantastic for organizing this. So thank you to the organizers as well. So the journey today is called a progress on navigating the mind-body continuum for musical expression. I gave a similar presentation a few years back and set the stage for what I'm going to talk about today with some of the progress that we've made and some of the new developments that we've made over the last couple of years. So I'll be introducing those and hopefully relating them a little bit to some of the work I saw just in the last session. I mean, it's fascinating for me always to see the new work being done in the new interfaces for musical expression genre that's so close to my own heart, and that the problems are still incredibly hard as far as research goes. And they illuminate so many deeper insights into human expression. And so seeing some of the student work, and I read through some of the titles, saw some of the presentation, is very encouraging for our field. So hopefully some of what I talk about today, some of it is somewhat theoretical, so I'll try and make it a little more entertaining than it probably looks like, but relate it to the NIME work that many of you are involved in. And so that's how I've structured the presentation today. So just some of it's a bit of a history lesson. I've played these videos before, but some of the work I did, and I think this may have been, I forget where this was presented, but some of the NIMEs that I've worked on, like the two-person flute, and looking at how two people's intimacy and through this connected instrument led to different forms of expression, as well as new ways for them to think about their own musicality, was very important and formative in ways of thinking about expression. So that work showed up at NIME, but there were other works at NIME as well that really looked at how the performer and the instrument worked together, coupled to an audience. So in this one in particular, the audience plays an important role in understanding the expressive intent of the two performers. Because the audience, the idea was that they get a vocabulary of the two people working together, and it's kind of icky because they're sharing breath together. But that leads to that acknowledgement of the effort and a construct between the players and the audience that leads to a new form of expression. And it kind of worked. I was in the audience while this was being performed, and there are quite a number of people going, that is just disgusting. And so that's great. That's what I'm looking for. So my own work in terms of way back when, I show this all the time because it's really the core of what I've been doing. That should be a little louder. Let me just back up there. So my own work with Glove Talk 2, I play it again because there's so much still I learned from it.
I am Sam. I am Sam. Sam I am. That Sam I am. That Sam I am. I do not like that Sam I am. Would you like green eggs and ham? I do not like them, Sam I am. I do not like green eggs and ham. Would you like them here or there? I do not like them here or there. I would not like them anywhere. I do not like green eggs and ham. I do not like them, Sam I am. Would you like them in a house? Would you like them with a mouse? I do not like them in a house. I do not like them with a mouse. I do not like them here or there. I do not like them anywhere. I do not like green eggs and ham. I do not like them. Sam I am.
So that's Sagif playing with the Glove Talk 2 system, and he spent 100 hours, or not 100 hours, about 100 hours learning to speak with this and sing with this. And it was interesting because it's a continuous mapping using a machine learning algorithm to adapt the relationship between what he does and the sounds he produces using an artificial vocal tract model that he could play like a musical instrument. And with practice, he could speak and sing, not perfectly or not a bit robotically, not naturally. But there were many insights still from this work that led to a number of different research directions that I'm going to talk about. The couple surprising phenomenon was that it was quite expressive. He's able to, because it's not words he's producing, it really is sound, like a vocal instrument, a voice instrument, that he can go, uh-huh, or and these non-linguistic sounds, and he was able to control them expressively to get the intent across, which was probably a good thing because sometimes it was hard to say the words anyway. So that was good. So that tradition of a voice instrument that is continuous control like a musical instrument, but in the vocal range, that actually has a long history, say compared to, say, sign language or something, sign language recognition to produce words. So we can go back to, the 1800s with Joseph Faber's work and Alexander and Melville Bell's work and von Kempelen's work in the 1700s and electronic versions of these synthetic voice instruments into the early 1900s, with a very famous one, the Voder, which was this hand-actuated keyboard with a wrist bar and a foot pedal for pitch. Glove Talk 2 used pitch in the hand, but this uses a foot pedal. Keyboard, a year's worth of practice, so it's not a simple thing to learn how to do. Done in 1939. And I have to switch to YouTube because for some reason it didn't seem to work as an embedded video. Here's what it sounded like.
The machine uses only two sounds produced electrically. One of these represents the breath. The other, the vibration of the vocal cords.
That's a chordal keyboard.
There are no phonograph records or anything of that sort. Only electrical circuits such as are used in telephone practice. Let's see how you put expression into a sentence. Say, she saw me, with no expression.
She saw me.
Now say it in answer to these questions. Who saw you?
She saw me.
Whom did she see?
She saw me.
Did she see you or hear you?
She saw me.
So you get that sense. This is 1939, right? It's very impressive. And yet some of the concepts and challenges we're having today with NIMES and creating new forms of musical expression, or in this case, voice expression, using these different types of interfaces and the control of them remain today. Like even that one, it's a bit sing-songy actually. And when you hear it, other speaking, it always has a bit of a sing-songy notion behind, or tone to it. And I think it's because of the foot pedal. A foot pedal for pitch is actually quite challenging to control, get those trajectories that sound more like a spoken word versus a sung word. Plus a year's worth of training for that. That seems quite excessive given that they already knew how to speak. So this is our challenge, and this has been my challenge through my career, is how do you make this thing sound natural? Not this robotic sounding or sing-songy flavor. It must have something to do with control the ability to be able to control for the person to play it in a way that gets the a natural sounding voice? Or is it something in the synthesis engine, or something in the mapping, or everything? Still, 100 hours is a long time to play. It's not that long for a musical instrument to learn how to play that well. But for voice, well, we already know how to speak. We already know if you're, a vocal person, you already know how to do all the control of your articulators. So why does it take 100 hours? How long should it take? How can we make it easier? These are at the heart of the same questions when we augment our instruments with hyper instruments or create a new NIME of some sort or other. Somebody's going to have to learn to perform for it, with it. And how is all this stuff working in the brain? Because that plays an important role in terms of how that expressive content is going to be developed and performed. And if we could have a better understanding of that, maybe we could make it easier. Maybe we could find a better pathway from intent and meaning to a listener. So these are the heart of issues for me, and here's how we approach them. So first step, let me just go back to that little video. Yeah, so the first step was thinking, well, these synthetic articulatory or synthesizers, speech synthesizers, they come in a variety of flavors, and one of the flavors is like a formant synthesizer with amplitudes and frequencies that you're trying to control, in his case with the hands. Those are not actually the same as what the vocal tract does. The vocal tract uses a pressure wave through a vocal fold vibrating to get a sound source signal that's then shaped dynamically by the vocal tube, right? And there's a lot of physical constraints associated with that. You can't just jump around in the acoustic range because of the relationships, all the physical constraints here. So maybe plays a big role in what it means to be natural, and if we could capture that. So that led down an entire pathway to model the upper airway as an acoustic tube with the vibrating vocal folds, so that a human controller playing this thing would then control the artificial muscles, the computer simulated muscles and lung pressure and tension on the vocal folds to get the speech signal to come out. And so all those physical and mechanical constraints here place, think of it as a topological constraints on the control space to make sure that as you move through that control space, you're going to get speech, which also means you can't get other sounds out of it, but that constraint can make it easier to play. So when you think of your own NIMEs and you hook up, say, sliders or a mouse or some other controller input, you have this mapping, right, to the parameter space of your soundscape. But if that's arbitrary, it's going to be very hard to learn. And Marcelo has done great work in looking at that type of mapping problem and what is it, how that relationship should work to capture those expressive intents without requiring a lot of effort. Bill Buxton liked to say, use the term 1 + 1 doesn't equal 2. So when you have two sliders, say, trying to control to draw a circle, that's kind of hard. Like Etch-a-Sketch with two little knobs, drawing one in the X direction and Y direction, and try and draw a circle, that's quite hard. But if you need to draw straight lines, it's pretty easy. In contrast, you would always say that the magic pad, which is that wax substrate with the paper on, with the wax, the film on top or the plastic film on top, and you draw with a pencil or a stylus, you can draw a circle quite easily. But if you want to draw a nice straight line, it's actually pretty hard. You need a ruler. So just saying I have two 1 degree of input devices to control a 2 degree of freedom output, say some musical parameter space, they need to be matched. And by creating an artificial vocal tract that is based on the biomechanics of speech, the idea was to make it an easier control space. for the range of speech and voice. So that led us down having to build such a thing. And that's been an ongoing endeavor. So that's what this is trying to show here. So we built this artisan framework or toolkit. Works a bit like a cookie cutter Tinker Toy type thing. You bolt things together and you combine like finite elements for like soft tissues like lips and tongues and rigid bodies like jaws, so that you can then have synthetic muscle activations, computational muscles that then actuate the jaw and the tongue and the lips and so forth to get the acoustic tube working. So we put these all together, and they can do things like breathing, chewing, and swallowing, but speech is really our end goal for this. So you put all these together with this toolkit. That's a video of some of the things it does, and it's free to download if anybody's interested in working in the biomechanical modeling field, say for an instrument or a flexible instrument. You can actually build them with these. The reason we put finite elements with a rigid body is to get the speed, because finite elements take forever to simulate. Rigid body, though, don't give you very good soft tissue type models. And you need both, so by putting them together, you can get computational efficiency on the rigid parts and just put enough in the soft tissue parts to make it run in real time. So that's what Artisan supports. Anyway, I won't play the whole demo reel, but you get the idea there. So all of that was so that we could build this human head model that we can then simulate the sound through it. So here's just our Frank model, which we use as our basis and improve on that or take parts of it. So that's just a vocal tract head model that has these red lines are the simulated muscles, lines of action. You can make those finite elements, but generally speaking, we just use line-to-line, point-to-point muscles as lines to actuate these things, except for the tongue. The tongue is very complex. So that gives you an idea of what the head model looks like. So that gets you the biomechanics. All the constraints of the upper airway are somewhat captured in that head model. And we're continuing to work on that. This is a long-term project to get those two all work well. So now once you have the biomechanics of the head actuated with these synthetic muscles, you now need to get the sound out. So that's now an aeroacoustics problem, which is kind of like modeling your woodwinds, where you got a tube with some reed excitation, for example. But in this case, we have vocal fold excitation. You do have some other excitations like a sh or a s. So there is some sound sources up here, but for the most part, we think in terms of sound sources here as a major part of the way of modeling things. So we need to get that synthetic vocal tract and simulate the aeroacoustics through that. So that's a whole another project that we've been addressing as part of our brain to speech project work. So the challenge is that there are one-dimensional models, like simple waveguide models that we use in our, like for a clarinet model or something, you might use a one-dimensional model, and it works quite well for many instruments because they're rigid. But as soon as you start to have soft tissues and bent models with three-dimensional structure that are varying over time, those one-dimensional models don't follow the geometry anymore. So you need to tune them somehow, and that's not possible when what you're trying to control is a real-time change of a synthetic vocal tract. So we needed something to do those aeroacoustics. 3D models, they exist as well, but computationally to do even 50 milliseconds takes hours and hours of computation time. So you're not going to be able to play it. It's too slow. So we wanted something in between that would run in real time. And so this led us to create what's called a 2.5-dimensional model. Though a couple of years ago it was a 2D model, that wasn't quite sufficient to capture the geometry of the vocal tract. say, a cross-sectional slice of your vocal tract in 2 dimensions, didn't quite capture enough of the geometry, especially the acoustic effects in the higher frequency. So we added an extra dimension, or half dimension, by lumping in a depth. So just to remind you, what the 2D looks like are just your pressure and velocity equations to simulate pressure and velocity of the sound wave. And then you have some excitation that you model, and just some boundary conditions there. And in the end, you can get this thing to make sound. That's not making sound, is it? Okay, well, I have another video of it making sound. That was supposed to be like just a single sinusoidal sound. But those are the basic equations that simulate the wave propagation in a medium of some sort. And you can use a GPU to accelerate those equations using a finite difference approach. And that can run in real time. So we published on that, but like I say, this approach doesn't capture the geometry effectively when you do it in a 2-dimensional. So what we did is we lumped in the depth parameter. So when you look at a vocal tract, here's a simple representation of just a bunch of circular tubes stacked on top of each other. And that's really what the 2D representation was doing. But really, a vocal tract has depth along its along the Z dimension. Like as you move along the vocal tract, there's different depths. It's not just cylinders. So this lumped depth parameter allows us to get more sophisticated geometries and still keep the computational efficiency. As soon as we go to a non-lumped version, that's the full 3D, we lose all the computational advantages, and then it's just super slow. So that's something that really we've refined quite a bit since the last time I spoke here. So it does support mirror symmetric geometries, which are very common in speech. This gets us out all the way up to 12 kilohertz. That's pretty good, which is for male and female voices in a vocal, like a speech range, is pretty good. Probably not sufficient for some singing types of sounds and other types of extended voice, but for speaking, that should be sufficient. It's sitting at about 10 times slower than real time. So 50 milliseconds takes us around 700 milliseconds of computation time. But we have a pretty good idea how to speed that up to get that into a real-time causal simulation, which is what we need so we can play this thing. So we're still working on the curved tube side, the parallel tubes. So you do have nasal cavities and other sort of parallel cavities in the vocal tract to give you more natural sounds and more vocal range. Those are relatively straightforward to do with this finite difference technique, and we should be able to keep the computational. It's about getting the domain a little bit bigger, so we have a pretty good handle on that. The moving boundary problem, that's a very challenging problem, because when you're playing like a woodwind, the walls don't really move unless it's like a trombone where the length of the tube is changing, or a slide whistle. For the most part, it's pretty static. But when you're talking and doing voice synthesis, your vocal tract is moving all the time, and that's acoustically, that's very hard to simulate that. So. And then additionally, we're working in this domain with this 2.5D solver, so we really have to adjust the methodologies for the moving boundary and make them computationally efficient. So we use an immersed boundary method for those who are interested. That worked quite well, but computationally a bit slow. So we need to simplify the immersed boundary method a little bit to make it fit within the GPU so that we can keep the real-time nature of it. So that's kind of where the obstacle is right now on the moving boundary problem for dynamic tubes. And the mouth radiation, that's another challenging issue, because as the sound comes out into the space, as we saw in the getting the mute, getting that mouth radiation, the last talk in the last session. The sound coming out interacts with the environment. And so that's also a very important phenomenon when you're speaking, and capturing that is not so straightforward. So we're working on that as well. All this is done for the vocal tract, but these techniques could be translated quite easily to other instruments that have any two-dimensional structure, like a drum head, or imagine a flexible wind instrument of some sort. A bendable clarinet or oboe or something like that. That'd be kind of interesting to play around with. So it's all the same equations for that. So just in case you're interested, these are the lumped depth parameters. So it's depth in the x and the y dimension that are just a single parameter. And that's just added to the equations. If you're interested in that, we can talk about that some other time. So all this is so that we can model this funky vocal tract here and from 3D into a two-dimensional geometry with depth. And the depth changes over the x and y grid. And that's what we're able to simulate. Just so you can, don't know why this isn't playing sound. That's supposed to be sound there. Do we have sound? That's just weird. Okay, well, we'll have to get back to that sound. It's not that exciting of a sound given that it's just a sine wave playing. So you would hear a sine wave and this little red or magenta color here, that's a simulated microphone, and you can move the microphone. You can put in walls, and it's just showing that the simulation makes sound. Here's where we used it with Victor Zappi's and Deb Mohotra's work on the hyperdrum. So we use this for the drum, for these dynamic drums. So that's just let me pause that, oops. So that was a giant touch surface that you could draw drum surfaces and have different types of drum properties. And then the simulation engine is just simulating an acoustic wave propagation in that two-dimensional space. So what you're actually seeing on the surface is a slowed down visualization of the acoustic waves propagating around and interacting on these drawn drum surfaces. That was called the hyperdrum. But it's just to give you a flavor that you can use the simulation engines for a variety of different acoustic effects and control them in real time. At least that's making sound. Maybe I'll just advance that a little bit so you can sort of see it played.
Controls. Properties of the simulated means creating 2D percussions of different materials. This feature can be combined with the ability to change size, shape, and type of boundary to create a wide variety of percussive sounds. Several percussions can be simulated at the same time, as the domain can be split in different areas, each with a dedicated microphone, specific boundaries, and acoustic properties. The graphic editing mode permits to select individual areas and assign the local settings. Portions of the space enclosed in boundaries can be quickly turned into new areas with one touch.
Yeah. So you get the idea of what those equations are trying to accomplish, and we're doing that for voice. My message for the group, the NIME group here, is to think through your simulation engine, actually, because we're all using, under the hood of our NIMEs is typically some synthesis engine. And by changing some of the possibilities and the way that simulation works, it opens up different possibilities of establishing the relationship between what the performer is going to do and what the sound is, and imposing certain types of constraints that are consistent with the expression that you're looking for. So, so that's worth spending a little time looking at that, so you don't feel constrained, say, by some prefab synth in a MIDI engine or driven by MIDI parameters of some sort. So it's worth investigating that. So, okay, so that's the artificial vocal tract. That's the work we've been doing there, getting the aeroacoustics working, get the biomechanics working. The next part is, well, we're going to try and control this thing, right? Whether it's through gesture or in the work we're doing at UBC, we're also doing brain-based control, so ECOGs or EEG. Well, how hard is that problem? That's like asking, how hard is it to play the piano? Or how hard is it to play a violin? Well, how hard is it to speak? Well, this is an unknown question. So just to give you an idea, so in English, there's a little tongue twister there you can try, or in French, there's another little tongue twister you can try and say. Why is that so hard? Say it fast. That's hard, right? So how much effort does it take to say stuff? And why are some things harder than others? This is on the exam, just so you know. So that is a very fundamental question. It seems like such an obvious question, especially for a group who's involved in the NIME world, as everybody here is, in some form, or in the performance world, where this is why you practice, right? Because there are some things harder to play than others. But in speech, we just take it for granted that it's all, oh, it's easy, I just learned as a kid. How hard can that be? Yeah, well, it's not so easy, and we don't have quantifiable numbers for how hard it is. If we could quantify how hard it is to speak or play some instrument, then we could use that in an optimization function so that the player could play, get some sound out, and then use some machine learning to optimize it to make it easier to learn to play or easier to play, right? And if we knew where the tongue twisters were in our expressive space, we can make those easier by changing the statistics, or just make sure that those are kept out. But we don't have that for speech. That doesn't exist in terms of quantified numbers. So that's what our group has been working on quite a lot, to try and figure out what the challenges in terms of motor control and the articulation of voice. And the same principle applied not just to voice, but to other performative systems, whether it's through gesture or a brain-to-computer interface. So that's me in the EEG setup as we try and figure this out. So we're looking at UBC in my lab at embedded sensors in the brain, as well as EEG, which is surface. And if we could get access to a MIG machine, anything that tries to get at the motor control, the speech motor control regions of the brain, as well as some of the brainstem control of the vocal apparatus, includes like breathing and tongue movements, get those activations and map them into these artificial vocal tract controls. We also look at gesture. That's still very important to us. And figuring out, well, how much information you can produce over time, whether it's from an EEG signal, which is pretty poor, as we all know, versus, say, your gesture, your hands, which for controlling musical instruments or playing music, and that's also an important point. Some instruments are easier than others. But how much can a person generate? And how much do you actually need? So like a kazoo doesn't need as much information as a violin to play well. But how much different is it? So we're focused on voice, but the same principles apply. So we look at the whole system to figure out how much information is needed. And we look at speech as a deep brain function here with various sensors to hear what you're saying, whether you hear it or feel it, and it gets processed, and then you have motor control from the brain going into various lower order muscle synergies where certain combinations have been learned over time, and they get solidified within a few years of of your speaking life. So those get, that Etch-a-Sketch, those pairing of parameters get solidified in your brain. And then there's the biomechanics of your tongue and your jaw and so forth. And those things all move. And out come the aeroacoustics. So that's a whole chain of control. And then that goes to a listener. And the listener is also part of this equation. So they see you and hear you, probably both together. And they're sending you back signals of whether they understood you. So you go, so you know what I mean, right? Uh-huh. And everybody is on board. You didn't need to waste a lot of information spelling out every single concept. When the listener kind of knows what you're talking about, you go, yeah, huh, uh-huh. And so that's a very low information amount of control that's needed for that. But if the listener doesn't understand you, then you're going to be spending a lot of information to get what you need to say. It's obvious when you're speaking a different language, how much more information is needed. And the human brain is very flexible and very dynamic, and it figures all this stuff out for you without even thinking about it. So where do we see this? Where do we take our lessons? We take our lessons from Fitts' law. So if I know this is where most people, including myself, typically think Fitts' law is kind of boring. It's in the HCI world, and we know we're supposed to know it and study it and that, but it's kind of boring because it's this principle that just is very isolated about, well, how long does it take for you to go from one point to another point, the reciprocal pointing task. And as Fitts showed, that the dependence on the distance you have to travel between targets, obviously the bigger the distance, more time it takes. But the weird thing is the wider, the bigger the target, the faster you are. So you can, if it's a big target, you can just ballistically move there and you're going to hit that target. And your brain is figuring this out because you make that target a little smaller and it takes longer because your brain is dynamically adjusting to the fact that it's a harder thing to hit. So it's going to have to put in some controls that as it's looking like it's going to miss, it's going to have to be correcting. And so it takes you longer. And if you play a video game, you know the little small things are much harder to hit than the big things. So Fitts just quantified this. And you can interpret this in terms of information theory, whereas the amplitude, the distance is like the signal, and then the noise is like those widths, how big they are or how small they are. And Fitts just came up with a very nice principle that just showed that you can double, if you double the width, you can have the distance and it'll take the same amount of time. So that's wonderful if you're sitting there just poking away at pieces of paper, but how does it apply to your tongue? Or in the case of a musical instrument, when you're trying to play, like, why are the piano keys the size they are? What if you made them smaller or bigger? Does it make it harder? And if we made them smaller, okay, it is harder, but you have less distance to move. So it should be a little faster. I don't know. Something to investigate, right? Anyway, so that's, when it comes to speech though, there's lots of constraints in here. It's not just some arbitrary thing. Like your tongue, if you need to make an S, the tongue has to go up towards the palate, form this little tiny gap, small enough to get some turbulence, but not too small that it blocks the air, not too big or you don't get turbulence. So it's very precise there. But you've got this curved palate typically. And if the tongue was just curved the right way, you could just slam it right into the palate and it'd just be perfect. So the target in that space is maybe big, but the target in the little gap is actually very small. Which is it? What's the brain dealing with? So there's lots of hard constraints. You've learned languages over time, so there's motor programs embedded in your myelinated sheaths of your motor control pathway. Those were learned early on. You have perceptual feedback control and ballistic control that your brain's able to monitor and manage dynamically. And there may be some predictive modeling going on in your head. As you practice, you start to know So when you get good at sports, for example, you don't need to look at the ball and where your racket is. You know the trajectory and you can predict it, because if you couldn't, you wouldn't respond fast enough, and that happens with performance. So we want to figure that out for the brain. So figuring these things out. So the Fitts law is really just this simple pointing problem, but there's extensions of that that include, well, what happens if there's a brick wall constraint? That's like your palate and your lower teeth and your jaw can only open so much. Then you have these other properties that in the perceptual world, when you're saying like an E sound, just as an example, an E, that's sort of a plateau. You can make kind of anything E-like, and the listener listening to you will know from the context what you're saying. So in fact, if you record a speaker and a listener who are very tuned to each other, and they're speaking fairly quickly, the vowels all just kind of are like a schwa, like a It's just a with a little consonant in there, because they don't need to move very much because the listener's correcting for all that. So you don't need to move so much. That's playing a role too. So we did some work to look at how much that affects this movement time, this control of your tongue or control of gesture, to say, yes, that actually makes a big difference. In terms of Fitts' law, it's really reducing the index of difficulty of the task, which then improves movement time. And our latest work was on trajectories. So when you're speaking, it's not like you're moving linearly. You move through these trajectories, especially when it comes to things like diphthongs, like I and O, ow, and you. So these trajectories, actually, you need to get them correct, or the perceiver is going to hear like two different vowels. Or you'll go through like a schwa to an E, and it won't sound right. And so that's a control problem. How hard is that? Well, we just characterized it in terms of this curviness parameter, that in fact you can account for movement time with these curvies. Why are we doing all this? Well, because we're looking for an objective function so that we can then get people to make the gestures, play the sound that you want to make. They can record some gestures, do that over big corpus of sounds and gestures, and get a machine learning system to optimize the task difficulty, the index of difficulty, to impose constraints where the statistics suggest they are, to put in the equivalent of motor programs, so you can draw these curves in a much easier way so that you get these trajectories. So that the overall effort needed, the amount of information per unit time that the brain is required to control, is minimized. And then we argue that's what's going to make it easier to learn to play or to speak. And we argue the brain is doing that with speech when you're learning to speak. So I just said that. So lower that information, index of difficulty of the task, make it easier and easier, requiring less and less information, so that when you're learning to speak or sing or control voice, it becomes an easier task. So that's the whole idea, and the basic hypothesis that drives all our experiments is really that learning motor control includes all these constraints in the representation, and that's what humans are doing, and that's what we want to do when we're building this system. And I would argue for many of the types of things we see in the NIME world, where it's a question of mappings between what a person does and what they're putting out, the same principles apply, because a performer is going to have to learn to play this thing. And if they already know and it's an augmented interest, well, now they're going to have to adapt some new principles, new way of learning to incorporate those. And if it's some crazy new NIME thing, they're starting from scratch. And how can we make that easier versus just hooking up sliders to the acoustic parameters and throw somebody up on stage, which We see a lot of at NIME. So just to summarize that, and then I just have a little bit more after this on just some other topic. But just that chain of motor control for speech, there's a chain of motor control for expression, whether it's a facial expression, musical expression, or voice expression. We argue is all about minimizing those information requirements. And you need to think through the chain. For music, it's complicated. Speech, everybody who speaks the same language is an expert listener. That's not true of somebody in an audience for music. You don't have necessarily a shared understanding of the musical vocabulary, for example. So that's a place we can look at. But just this continuum of motor control for that performer is also really critical to incorporate into our models of NIME mappings. So yeah, just said that. And then that's where machine learning fits in, is that, with enough data-driven approach, you can do a data-driven approach to help along the path there. So that's the side that we're doing on the brain to speech. Just want to talk very quickly about the other side of the things we're doing around the visual sides and VR and AR, XR, various other Rs. Really looking at how we bridge the real and virtual to make the virtual fit into the real world, real going into virtual. So we've been playing with that. This was our spherical display, which is not an immersive display. It just sits on the table and you can walk around it and it looks 3D inside the space here. So we've been playing around with that. And an offshoot of that is really what I want to talk about. Here's just a collaborative version of it. But this idea of taking these virtual worlds and bringing them into real and our real into those virtual worlds. And it is somewhat consistent with control of these artificial spaces. So here it's just where we're pointing from the virtual world into the real world, and how accurately can an avatar point at something into the real world. A very peculiar phenomenon is an avatar from a virtual avatar in 3D pointing into our real world. You actually perceive they're pointing better than a real human pointing at the same object. It's kind of a weird phenomenon. And then just things like eye contact, which we've been working on as well to get that expression from the virtual into the real space. But the thing I want to talk about today that's an offshoot of that is the work we just presented called Halo Touch by a student I co-supervised with Robert Zhao, so that's Kaseya Xia. And it's called Halo Touch. We're kind of excited about how well it worked. So this is just a video of it. There was sound. There's his sound in there somewhere. Just explaining it. Supposed to be sound. Oh, there is sound.
Input system on general surfaces that supports touch sensing, proximity sensing, and pressure sensing. It can even work in extreme conditions like a watery surface. Halo Touch does not need to instrument surfaces or add sensors to users. It achieves a 99.2% touch depth accuracy, a 5.5mm spatial accuracy, 150 milliseconds latency, and a 4.97mm touch point threshold, and it works on most of the general surfaces that reflect infrared light. Beyond those capabilities, Halo Touch also supports advanced features like pressure sensing and proximity sensing. Halo Touch is a comprehensive touch sensing system.
So it works. Oh, I thought I had a little explanation of that. So the way this system works is when you have infrared sensors, like you do on the HoloLens, for example, used for like gesture tracking and that sort of thing. That infrared, when it hits a corner, like a finger touching a surface, the infrared interferes with each other, and you get this little halo of light in front of the finger or whatever, making the little corner. And it's that little edge that we're detecting. I think there's an image of it in here. You can see in here somewhere. Where is that? There it is. It looks like that. So the camera sees this little halo. And that you can use to tell whether you're touching or how far away it is, and from any surface. And it can be used for multi-finger as well. So that's the effect we were using. Something you might find useful in your own work for, say, some musical interface, say a drum interface or something like that. It does give you distance, pressure, and the contact. And the reason it's 150 milliseconds is because the most of that's from the camera. So a faster IR camera, you could probably get that down to the 10, well, maybe 10's a little optimistic, but 50 milliseconds anyway. So a 200 hertz camera could do that. So anyway, that's out there. If anybody's interested in doing something, some NIME with that effect, we'd be totally interested in getting involved in that. And all of this is part of what I call the VidX group, where we're looking at visual representations of varying flavors, and in particular, video as well, video as a first-class citizen, trying to make video mutable, interoperable, and bidirectional. So that's another aspect of expression that we look at. So I argue that video, to be really a medium, a first-class citizen of media like text, we have to be able to speak video. I send you video, you send me video. I can copy paste video into text into video, and that all makes sense. That requires a whole new literacy and a new technology to support that. Essentially the equivalent of the pen and pencil for video. Or sorry, the pencil and the eraser needs to be figured out for video. So we've been working on that quite a bit. So that it can really emerge as a full, in our case, being an educational institute, an educational medium, a much better one. So we've been working on that quite a bit and different ways to look at that. This has naturally, and there's a little argument or a little provocation for your own work, is around these generative AI models. I haven't talked about that much because it's not impacting our other work, the expressive work, so much, but where we're seeing it having a huge impact is in video and time-based media expression. And it's those tools of the large language models, generative AI models, and some of the vision-based models that can be used to extract content, extract meaning, and compose. I'm sure you're feeling this too. Compose content, both in image-based, but in time-based medium. And becoming good at articulating what you want and what you need has become a very important part of what we're seeing through the use of video in our educational contexts, which is where we're looking at video as a first-class citizen. But it's much beyond that. And I don't have time to talk about some of the implications of that, but I think for us as creating NIMEs and composition and playing and what is expression, I think it's having if it isn't already, will be having a very profound impact on that. So it's something to put on your to-do list if you haven't already. I'm sure you have. So I guess I'm kind of at the end here. The other point I tend to make around putting these things together around expression is the aesthetics of interaction as part of your design elements in creating your new interfaces for musical expression in your performative side of things. And I always argue that you want this intimate relationship, and you want to put the infrastructure in there to allow your performers and your audience to have that intimate relationship between what they're doing, what they're playing, and what they're hearing. And it's very related back to the way we look at the continuum of voice control and the brain trying to communicate meaning and expression to the listener. And that the aesthetics of that combination are also playing an important role, and that we design that as instrument designers. So I just look at these 4 different aesthetics that all should be part of design of these new interfaces for musical expression: the response, the control, reflection aesthetics and belonging. And belonging is a much more challenging one, but it leads to much deeper expressive capabilities for your performance with your instruments. So I do argue these things are coupled, sound and image, time-based media, those are tightly coupled. We shouldn't be thinking of them independently. And so that leads to some of these aesthetic principles. Definitely for voice is also an important element of expression and voice. So all this work is done as a team. So I have quite a large group with the brain-to-speech group here and modeling, and then the machine learning and representational group. It's another big team with lots of collaborators. It's a wonderful environment. And then the VidX group dealing with video and some of the expressive forms that video is taking, not just education, is also a big group. Lots of industry partners along the way, and obviously our Tri-Council funding as well, so want to appreciate that. Faculty, postdocs, graduate students, undergrads all play a very important role in the contributions that our lab, or my lab, is making. So thank you very much for your attention, and love to have conversations afterwards.